Good afternoon, everyone. Thank you for joining the Electrical Safety in LV Switchboards webinar. My name is Jamela Johnson, and I'm the Marketing Coordinator at Rexel. Your speakers from Eaton today are...
Hi there, I'm Drew Clough. I am the Product Marketing Manager for LV and MV equipment here at Eaton. I'm joined by my colleagues Tarek and Adam.
Good morning. My name is Tariq Hussain, and I'm a low voltage applications engineer. And I've been with Eaton just coming up to 13 years, mainly working on low voltage distribution equipment.
Good afternoon, everybody. My name's Adam Tennant. I'll be taking the complementary safety measures part of the webinar. I started with Eaton, which we used to be called MEM, back in 1986 as a technical apprentice. Held various roles through my service. Currently, engineering manager and standards manager for the power distribution division of the UK.
So a bit about Rexel. We are 90 years strong in the industry, 18,000 years of experience, 200 branches across the UK, and over 2,000 colleagues. Webinars were introduced to invest in you all by supporting your progress as changes appear within the industry. Keeping updated is very important. Webinars are still new to us, with many more planned ahead, so please do keep a lookout. So the web shop. Rexel Web Shop is a brilliant tool designed to meet all your needs with 350,000 products online, view live stock across the UK, we have next day delivery, and many more. We work with leading manufacturers covering product categories such as lighting, energy solutions, site supplies, industrial controls, many more, and specialist products too. Before we get started, just to make you aware, this webinar is being recorded, and if you don't wish to be recorded, we politely ask you to leave. Any questions you may have, go into the chat box and we will be answered in the Q&A section. If there are any questions we cannot cover during the webinar, we will follow up separately. This webinar can be downloaded at the end. If you wish to receive it through email, please notify us in the chat. Thank you so much for your time. Now passing over to Eaton.
Hi, thank you. Welcome to today's CPD on forms of separation and electrical safety in LV equipment. This is a CPD approved webinar. It's approved by the CPD certification service. So the way it works is that you usually get your certificate in about 2 weeks' time. If you haven't had your certificate in about 2 weeks, please do get in contact and we'll see what we can do to chase it up for you. For those of you who don't know who Eaton is, we're a power management company, and we believe that power is a fundamental part of just about everything that people do. Eaton is a truly global company. We have customers in over 175 countries and supported by about 97,000 employees. We operate in two main sectors, generating sales of over $21 billion in 2019. The sectors are electrical sector and the industrial sector. And in the electrical sector, we have control and automation, engineering services, harsh and hazardous environmental solutions, life safety and security, power distribution and circuit protection, power quality, backup power and energy storage and structural solutions. And in the industrial sector, we have aerospace, automotive, e-mobility, filtration, hydraulics and truck. You can see we've got a very wide and diverse product mix supporting a number of vertical sectors, including data centers, oil and gas, renewables, utilities, and water and wastewater. But everything that we do and make is underpinned by our ethos of being a responsible and high quality manufacturer. So if you aren't already working with us, please do bear us in mind for your next project and see how we can help you achieve more. Before I pass you over to my colleague Tarek, I would just like to point out there is a Q&A or a question function chat box on the left-hand side of the screen, I believe. Feel free to ask questions as we go along, and then we'll have a Q&A session towards the end of the webinar. Over to you, Tarek.
Good afternoon, everyone. Hopefully today we'll cover on some key points on forms of separation within LV assemblies. I hope you enjoyed this presentation. At the end of the session, I'll be happy to take any questions. So let's make a start. So the first part is, what's the relevance of forms of separation? So forms of separation really the aim is to create subdivisions within a switchgear assembly. And these switchgear assembly, these subdivisions are generally created using barriers or partitions. And as a result of these sub-assemblies, we enhance the safety of a switchgear assembly by providing protection against accidental contact with live parts. It also helps reduce the risk of internal arcs, and also impedes the passage of solid bodies between compartments. Later on in this presentation, you'll see newer technologies of enhancing the safety of switchgear assemblies, but forms of separation is a tried and tested mechanical means of improving safety in switchgear. So a little bit about the history. So going back about half a century, the standard for low voltage assemblies in the UK was BS 5486. At the time, regarding internal separation, we had the class of assembly. None of these classes required the functional device, so your protective device, to be separated. Early 90s, the British standard aligned itself with the international standard, which gave birth to BSEN 60439. Regarding forms of separation, although the British standard adopted the IEC standard forms, there was a big drive from the large users of LV switchgear to provide more safer assemblies and give more clarity on the different types of forms of separation. So the large UK manufacturers collaborated and helped form the BEMA guide on forms of separation, and this was added as a national annex to the standard. Then in 2009, the standard updated once again to 61439, and again, regarding forms of separation, the main change was using the housing of a protective device as a means of separation. So there's three main components that we look at when we're looking at forms of separation. First being the bus bar. This is normally your main bus bar or distribution bus bar. Functional units. Functional units are normally your protective device, so this could be your ACB, MCCB, or a fuse switch. And external cable terminals. So these are what I would call the terminals where the customer connects his cables onto. And internal separation, again, we achieve this using barriers and partitions. These could be metallic or non-metallic. One important clause to remember is that forms of separation in the current standard are subject to an agreement between the user and manufacturer. Now, what this means is that there are various ways of achieving the same form of separation, different methods, different techniques. So that clause is really just to say that it's ultimately down to the user and manufacturer to agree on what method is the best method suited to them. So a little bit on the legal side. So most national standards are a harmonised document based on an international standard, and 61439 is no exception. Although it reflects good practice, it doesn't encompass the local legislations. Therefore, the standard is not legally binding. Specifically in the UK, we have the Low Voltage Directive and Electricity at Work regulations. These take precedence over the standard. Similarly, if you're joining us today from another country, you'll have your own laws and regulations in the country, and the same rules apply. So the main objective is to provide a safer environment for somebody gaining access to part of an assembly while other parts remain energized or live. So separating the assembly does this. So the first thing is that by separating it, we provide protection against contact with live parts in adjacent compartments. And this is normally done by creating an environment that is IPXXB in terms of its IP rating. Basically, in the industry, we would call that like fingerproof. And secondly, is protection against passage of solid objects. Obviously, the benefit of this is that it reduces the likelihood of, while if you're in a compartment doing some maintenance or something, it reduces the risk of objects falling through the compartments and potentially causing an arc flash. So in terms of design selection, so there's 4 main categories in the current standard. You got form 1, 2, 3, and 4. There's some subcategories known as like 2A, 3A, and 4A, and so on. And then there's the derivatives, type 1 up to type 7. I'd like to say that the derivatives are specific to the BS standard. In the IEC standard, we only have the main categories and the subcategories, and obviously in the BS we have the derivatives, the type 1s, 2, and 3. For those people who are interested in finding out how to design a system or what things to take into consideration, the BEMA guide has quite a comprehensive list of comprehensive guide on how to select the right type of form of separation for your application. It will run you through things like the environment the switchgear is going into, the level of safety you require, the level of downtime. And obviously there's things that you could take into consideration, like obviously the higher the level of separation, the more the cost generally, and also the footprint. Generally, again, the higher your level, your separation, the bigger the footprint of the switchgear. So we'll look at each form in a bit more detail. So form 1, I won't go into it. There's basically no separation between the 3 main components: your bus bar, your functional unit, and your outgoing cables. Form 2. So the main criteria for Form 2 is that the main bus bar is separated from the functional unit. So functional unit being your protective device. There's 2 sub-criteria. Form 2A. Form 2A basically means that you don't need to separate your outgoing cables from the main bus bar. And 2B, you do need to separate. And then you've got the type 1 and type 2, which is how you separate that. So we'll have a look at the next slide, which gives us some graphical representations. So form 1, again, as you can see, there's no separation between the bus bar, the functional device, and the outgoing cables. Form 2A, although it looks exactly the same as Form 1, but what we're using is the housing of the functional unit as a means of separation from the main bus bar. And you've got Form 2B. Again, we're still using the housing of the functional unit as a means of separation from the main bus bar. But here we're separating the main bus bar from the outgoing terminals using some form of sleeving over the bus bar. So this sleeving could be, insulation, could be, powder coating. It could be heat shrink or something similar to cover the bus bar. Then you got Form 2B Type 2. The only difference here is that rather than using some insulating material on the bus bar, we're using a barrier. So this could be, a molding around the bus bar or some kind of metal or metallic cover around the bus bar. So moving on to Form 3 here. So that the criteria here is that the main bus bar is separated from the functional unit. Each functional unit is separated from each other, and the cable terminals are separated from the functional unit. You've got 2 sub-criteria, 3A. In 3A, the cable terminals don't have to be separated from the main bus bar, and 3B, the cable terminals do need to be separated. And again, Type 1 and Type 2, we'll have a look at these on the next slides. So here's 3A. So the main bus bar is separated from the functional unit using the enclosure of the protective device, and again the casing of the protective device is also being used as a barrier between each functional unit. This type of arrangement in the market is known as group mounted. Then we have Form 3B Type 1. Now, there's a couple of methods of ways of doing this. You can either do it as a group mounted or compartmentalized. Group mounted, obviously, we just spoke about. It's, we're using the housing of the protected device as a means of isolation. And on compartmentalized, we're now using an enclosure to separate each functional device. And obviously being type 1, so the main bus bar is separated from the external cable terminals using insulating material. And type 2, we're using a barrier or a partition to separate the main bus bar from the external terminals. Then we move on to Form 4. Form 4 is, I would say, a standard that's more in favour these days when it comes to, definitely when it comes to switchgear assemblies, but even on some smaller distribution boards now, customers want that enhanced safety. So you're seeing this used more and more now. So there's products in the market like MemShield 4, which offer, which is what I would call a typical wall-mounted power board, but it's got all the safety features of a switchboard in terms of the mechanical forms of separation. So you've got Form 4A Type 1. The main difference here is when we move away from Form 3 is that in Form 4, the neutral must form part of the functional device. It can't be a common neutral. The neutral needs to come into either a 4-pole breaker or needs to come into a compartment where the functional device is sitting. And also, the external cable terminals need to be separated from one another. So in this example, you can see that you've got a group mounted and a compartmentalized. Other group mounted are not very common when you come to Form 4, but it can be done. In a compartmentalized solution, you can see that the functional unit is separated from the main bus bar in an enclosure. Each functional unit is separated by itself from one another by the enclosure. The main bus bar is separated from the external terminals because it's got its insulating material, and each of the cable connections again go into the compartment. So on Type 2 and 3, Type 2, we're just moving away from insulating the bus bar by covering the bus bar with a barrier or a partition. And Type 3, the only difference here is that each functional unit must have its own gland plate. So we can't use a common gland plate to comply with Type 3. So Form B, Type 4. When we come into Form B, the external cable terminals need to come out of the functional compartment and come into their own compartment. So as you can see, you've got two compartments on the picture. You've got your functional unit sitting in its own compartment, and then you've got the external cable terminals also in their own compartment. So Form B Type 5. Here, you can see from the picture that the external cable terminals, they exit the functional unit compartment, but then there's I would say a common cableway for argument's sake, but what we're doing is we're using some insulated boots to cover each terminal to provide that separation to comply with this with Form B. Just on the previous one, on Form 5, you don't normally see this type of setup, or I certainly haven't come across this. I've never seen it really in any specs out there, so it's quite unusual. Form B Type 6, I would say this is now probably, along with Form 4 Type 2, Form 4 Type 6 are definitely the market trend these days. So here you've got your main bus bar is shrouded using a partition or a barrier. Your functional units are sitting in their own compartment, although it can be done as a group mounted as well, but it's not very common. and then you've got your external cable terminals in the wrong compartment as well. And finally, we have Form 4B Type 7. The only difference here is that we can't be using a common gland plate for all the cables. Each functional unit must have its own gland plate. So that's basically it. It's a quick overview of forms of separation. If you're interested in learning more and having a really good understanding on all the ins and outs, the Beamer guide is available it's free to download from the website. It's got lots of information, lots of ins and outs of how to achieve things and the things you need to take into consideration. Please consult that guide if you want to learn a bit more. And now I'll pass it over to Adam, and I'll be happy to take any questions at the end.
Okay, thanks, Tariq. That was quite a comprehensive run through of forms of separation. Good afternoon, everybody. I wish everybody's safe and well as yourselves and your families in these trying times. I see there's a few questions that have come in already on the chat. So I think just before we go on and move on to the complementary safety measures, we just take a few questions on forms of separation, and then if there's any more as we go through the presentation, we'll take them towards the end. I know you mentioned during your presentation, Tariq, the trends that we see in the marketplace for types of forms of separation, and which ones are generally used in terms of type group mounted or compartmentalized, and what sort of rating of form of separation do you generally see in your applications?
Yeah, I think when it comes to any rating traditionally above 800 amps, you quite often the assembly was either a Form 4 Type 2 or Type 6. But I think things are changing now. I mean, obviously that's been the case for quite a while, but the market's always looking to have products out there that are more safer for the user or for maintenance purposes. And obviously, forms of separation offers that mechanical safety in a board. So I think there's products out there. I mean, like the MemShield 4, which is a panel board, essentially a panel board, but it's got you can achieve from up to a Form 4 Type 6 group mounted or compartmentalized solution. So yeah, I mean there's certainly a change. I mean, when it comes to like Form 1 and Form 2, you don't see those type of installations in the UK anymore. But market is definitely heading towards Form 4 now, I would say.
Okay, so I'll say another interesting one about sort of do you think there'll ever be harmonisation of the IEC standard Form A and Form B with the UK national annex?
I think obviously there's I think that, there's countries out there that are obviously becoming more safety conscious, just like the UK. I mean, the UK emphasises quite a lot on safety, so compared to some other countries out there. But I think as we see these countries develop and safety becomes more important, I think the international standard will also probably look to maybe take on board some of the enhanced or better clarified forms of separation that the BS standard offers. So I think with time, I think we might see changes. I mean, certainly I think in the new standard, the new edition that's been released recently on low voltage assemblies, they made an effort to give better graphical representation of the different forms to help people. So I think that, I see in the coming years there probably will be a change maybe on the IEC standard as well to enhance safety a bit more in line with possibly with the BS standard.
Okay, so I think we'll take one more before we go on with the complementary safety measures. What do you think the main challenges are for the customer when selecting what type of form of separation to be used are?
Yeah, I think with forms of separation, obviously they've been out there in the market for a long time now, so most customers are quite well versed with what they require and how to go around it. I think obviously the constraints can be the cost element and also the footprint at times. Switch rooms, space is a premium these days. So obviously, generally speaking, the higher separation you go to, the footprint increases. So those are, I think, some of the challenges that out there that for the customers. But in terms of application, the Beamer guide is a really good and quite a comprehensive guide on selectivity. So if someone is unsure, they can always look at the guide, and which would help them to come up with the right application. So yeah, I think obviously cost and I would say the footprint are probably two major things to consider for customers out there.
Okay, cheers. Thanks, Tarek. So we've now spoken about forms of separation and how this can reduce the risks associated with working on energised assemblies. So let's now talk about complementary safety measures that we can consider around switchboards and panel boards. So obviously there's several solutions out there in the marketplace today to improve the safety of our personnel. So even before we consider things about like forms of separation and arc mitigation devices, one solution is the deployment of safe working practices to reduce the risk to personnel. So at a UK country level, obviously the electricity at work regulations advocate some easy measures that everybody should really adopt. The first and probably the best and far by the safest policy is to adopt, don't work live on an electrical system or an assembly. Obviously, other good working practices are using the correct level of PPE. Arc flash studies can be carried out to sort of ascertain the correct level of PPE required, and this is a service that Eaton will offer if anybody's interested. Along with not working live, remote switching is another possibility. Obviously, that sort of takes the person away from the electrical switchgear, and the sort of opening and closing of circuit breakers can be done remotely outside the switch room. Other good practices are the standing clear and to the side stance, as shown in the picture. Obviously, if there is an event of a fault, in this particular instance, where the toggle of the multi-case circuit breaker is at the front of the switchboard, you will get some exhaust of ionised gases coming from the handle, around the handle area of the circuit breaker. So it's a good stance to adopt to minimise any sort of arc flash damage that one potentially could get. And then the other sort of good approach is the design of the PSC assembly, or PSC assembly is power switchgear and control gear assembly, or as it's commonly known, sort of switchboards or panel boards. We can sort of change the design to redirect any exhaust gases or pressure, have pressure relief flaps in the switchboard to put the gases away from the personnel whilst switching operations are taking place. Or the other good thing is by design, and obviously that's implementing the product standard of 61641. So let's talk more around about the IEC standard 61641, which is arc verified assemblies and protection classifications. And plus, we'll talk about sort of arc mitigation systems like arc quenching technologies in a little more detail in the following slides. So, as you can see, solution 2, this is where the switchboard is designed with arc ignition protected zones, or what we're commonly known as arc-free zones, and this is by application of design. So, for instance, on the incomer of the switchboard, you increase the separation distances between the terminals. Potentially you can use epoxy resin insulated bus bars between the incomer and the main bus bar. On the main bus bar itself, you can apply an epoxy resin insulation. Likewise, on the vertical bus bars, you can fully encapsulate it. So these sort of methods prevent, a flashover between phases if, a piece of wire or a tool was accidentally dropped on the bars, or there was some vermin that actually got into the switchboard during service. And then there's things on outgoing units. You can have unprotected circuits or protected circuits. This is where you can ensure that, within that compartment, the likelihood of an arc happening is reduced by, various methods you can apply, like insulating the internals of the copperwork. And then the enclosure itself, you can actually sort of incorporate a ventilation of the arc away from the operator. So under the IEC Technical Report 61641, which is a guide for testing under conditions of arcing due to internal faults, it identifies design features which will reduce the risk of arc flash hazards. So the arc ignition protected zones means remains a remote possibility that an arc can physically be generated due to the constructional barriers and insulation as part of the design. And so within the standard, we have 7 testing criteria. The first sort of testing criteria is personal protection, and this is achieved when criteria 1 to 5 are fully fulfilled. So the 5 criteria are that during the test, correctly secured doors and covers do not open. So during the test, they're usually closed and shut. In the event of an arc happening, they don't open. The next criteria is criteria 2. This is where parts of the assembly which may cause a hazard do not fly off. So due to the pressure that's been generated within the enclosure, things don't fly off and hit the operator during the event of an arc fault. Criteria 3, arcing does not cause any holes to develop in the freely accessible external parts of the enclosure, so below 2 meters. So this is sort of taking into account the average height of a person as a result of an arc burning through materials. As you can see in the picture, there's lots of black squares around the switchboard, and this really is representing the clothes of personnel. And during the arc flash test, if any of those cotton indicators were to ignite, obviously that would fail the test. But obviously if they remain intact, then that's a pass. And the last personal protection criteria is obviously the PE circuit of the switchboard is still effective after the event of the fault. So you've got the next criteria is personal protection and assembly protection is achieved. So this is criteria 1 to 6. And essentially criteria 6 is the assembly is capable of confining the arc to a defined area where it was initiated, and there is no propagation of the arc to other areas within the assembly. And plus the hot gases and sooting effects to adjacent units other than the unit that was under test are acceptable as long as only cleaning is necessary. And then finally, we've got the full spectrum of criteria 1 to 7. This achieves personal and assembly protection with limited operation capability after the event of a fault. So criteria 7 states that clearing of the fault after isolation or disassembly of an affected functioning unit in the defined area, emergency operation of the remaining assembly is possible. So, in the event of the unlikely event of an arc fault, you can still get the assembly up and running until such a time where you can have a proper shutdown and do the required maintenance and get the assembly back up to its fully functioning nature. So these criteria give assemblies what's called an arcing class, and there's 4 levels of arcing class: Class A, Class B, Class C, and Class I. So Class I really, the assembly provides just personal protection under arcing conditions, so it fulfills the criteria of 1 to 5 mentioned previously. Class B, the assembly provides personal protection and assembly protection under arcing conditions, and this is criteria 1 to 6. Then you've got arcing Class C, where you fulfill all the criteria 1 to 7. And obviously you've got personal protection and assembly protection, and obviously you've got the added advantage that you've got continued service after the event of an arc fault. And then finally, you've got Class I, so this is an insulated assembly, and obviously this assembly provides a reduced risks of arc faults solely by the means of arc ignition protected zones. So, you know, the likelihood of an arc happening within the assembly is very limited due to insulation of lines and you know, remote possibility of arcs happening. As you may notice on the picture at the top of the switchboard, there's a pressure relief roof that opens during arcing conditions, and the ionised gases vent upwards and are away from the operator. And obviously the IP of the switchboard is still maintained after the event. And as I mentioned, the cotton indicator pads are representing the personnel standing in front of or to the side of the switchboard during the arcing effect. Unfortunately, the video that's linked to this PowerPoint presentation doesn't work, but there are lots of videos on YouTube and the like. And if you Google Eaton arc fault protection, there's lots of information, documentation, videos that you can have a look at, and you can see the effects of a switchboard that's certified to 61641 and one which isn't during an arc fault test or incident. So what's the next solution? The next solution really is to reduce the fault clearance times. So typically, you know, if you rely on the air circuit breaker, which is generally an incoming device to a switchboard, it will operate probably around up to 50 milliseconds. And during that 50 milliseconds, you've got lots of effects by the arc. So if we consider the necessity for personal protection, we can see that, you know, if you look at the graph on the right-hand side, you can see after 10 milliseconds, the pressure reaches the maximum in the vicinity of the arc, and it's, you know, gets up to a level of around about 2,000 kilopascal. And then after about 15 milliseconds, the temperature of the arc reaches around about 13,000 degrees. So, you know, you've got you know, two effects that are really happening within sort of 15 milliseconds. So when you look at the consequences of the arc, about 50% of the arc energy contributes to the pressure build-up within the assembly because of the creation of ionised gases. About 35% of the arc is linked to radiation and heat conduction, and the remaining 15% is attributable to the burning of the conductor material at the point of ignition. So in a compact switchgear assembly, the pressure obviously can rise, you know, increase rapidly to a point where the enclosure can't contain the pressure, and the hot gases that are caused by the arc being generated escape from the weakest points of the enclosure, you know, and bend doors, blow doors off, bend side panels, and obviously impact the IP rating of the assembly and obviously the enclosures safely in terms of, you know, people being able to touch live parts potentially inside the assembly. Obviously, the arc produces a mixture of toxic combustible waste and molten particles, which are sort of generally liberated as copper, steel, and plastic components, which, are, you know, in the event of the arc, get vaporized if the arc is left to burn. This type of environment obviously is extremely dangerous to personnel in the vicinity, because the protective devices cannot operate fast enough to clear the fault before the build-up of temperature occurs when you're just relying on the ACB to operate. Hence why the classifications of assemblies A, B, C, and I, when tested in accordance to 61641, have been introduced. However, this is just a passive way of trying to mitigate the risks to personnel. There are some passive, active means of arc reduction. We can see this via sort of reducing the arc duration time. So if we're able to sort of stop the effects of the arc in 5 milliseconds or less. The problem is much less severe due to the log scale, as the pressure and temperatures will be obviously reduced. So what technologies are around to help us reduce this arc duration time? So this is where we use the implementation of arc quenching technology, which I'll discuss now a little bit further. And obviously in these more advanced systems, when an arc fault occurs, to reduce the clearing time, which also obviously reduces the risks to the equipment and personnel, they implement some devices such as arc quenching devices, which are sort of verified to the IEC standard 60947-9-1, and sensing means optical-based internal arc detection devices, which are verified in accordance with IEC 60947-9-2. And obviously these are implemented within the switchboard and some other technologies to reduce the time that the arc can be powered. So we've also got some other, Eaton have got also some patented technology called ARMS, which is employed on both their ACBs and their newly launched PXR multi-case circuit breakers. And ARMS stands for Arc Flash Reduction Maintenance System. So obviously, once the ARMS device is activated, the 50 milliseconds of operation is typically reduced to about half when activated. So obviously, again, reducing the amount of arc energy, further, and reducing the risks to personnel and obviously damage to the assembly. What you've got to note is obviously when you're including arc mitigation systems in assemblies, there's the new BSEN 61439 Part 2 and IEC standard now advocates 61641, a new standard called IEC TS 63107, which is a new standard which is the integration of internal arc mitigation systems in PSC assemblies, which really tests the application of these new devices within an assembly to make sure that it activates correctly under arcing conditions, and things like nuisance tripping and switching on directly onto an arc fault are all covered. It's okay just implementing a 947 device into an assembly and think it's going to work, but this new technical specification is one way of demonstrating that it does work. And then there's also a IEC technical specification 61439 Part 0, which is a guidance to specifying assemblies, and obviously that's within that technical specification there's lots of additional information about arc faults, how they occur, why they occur, and obviously ways to mitigate against them. So let's talk a little bit more about arc quenching technology. So this is where within the assembly an arc quencher is installed within the assembly to mitigate the energy supplying the arc, obviously to quench it as quickly as possible. So arc within Eaton's Arc-on system, the arc quenching technology is used in conjunction with the air circuit breaker, and obviously this reduces the arc time present. Obviously this is possible using the fibre optical detection and current monitoring, and of course the very clever arc quenching device that you can see in the pictures. So instead of just trying to interrupt the arc with just the circuit breaker, this type of system creates a dead short across the lines that mitigates the energy away from the arc and obviously quenches the arc in a really quick time. In terms of detection of the arc by the optical sensors and the current monitoring, typically typically takes around about 2 milliseconds, and then to create a bolted dead short across the lines takes typically another 2 milliseconds of time. So in the sort of, within 4 milliseconds, the arc then is sort of diverted to a dead short and obviously mitigated in the system. So this sort of reduces the time typically that an air circuit breaker would actuate in, and obviously in the background then the sensing equipment is also sending a signal to the air circuit breaker to open. So you've got a much more controlled system going forward. So let's just explain how the Archon technology works. So the first picture, what you can see is there's obviously several parts to an Archon system. You've got the detection, which is through the fiber optical cable running alongside the bus bars, in conjunction with some CTs which are monitoring the current, and you've got a piece of software that evaluates the signal, and then you've also got the arc quenching device itself, and then you've got the disconnection of the circuit. So picture one really shows the system in normal operation. Current sensors, the main incomer, the quenching device, the bus bars, the light sensors, and the master sensing unit all working passively together. So in normal operation, it works as normal. So in the event of an arc happening, the picture two that's just come on shows some light sensors detecting the arc across the bus bar, and obviously the CTs are picking up an overcurrent, and obviously then that sort of actuates the next stage. So the sensing unit then sends a signal to both the ACB and the quenching unit. Obviously the quenching unit activates and creates a dead short across the bus bars, which diverts the energy from the arc to zero. And then finally, obviously the main circuit breaker disconnects the supply, so the whole assembly there is then dead. So obviously the damage to the switchboard and personnel is obviously dramatically reduced, and obviously the continuation of supply can be quickly reinstated, reducing the downtime to a minimum, and obviously more importantly protecting personnel in accordance to the 61641 standard, fulfilling criteria 1 to 7. Just a note for you guys. The tests during 61641 are done with doors and covers all closed and screwed onto the assembly. The Eaton Archon device has been tested with 61641 with the doors open, and we still achieve criteria 1 to 7. So that's an additional safety aspect that Eaton have taken on board in terms of testing and costs to demonstrate that even with the door open, with the Archon installed in our switchgear, we're still meeting the criteria 1 to 7, where other manufacturers are testing with doors closed and covers on. Just something to bear in mind. We've also recently tested to the new IEC technical specification 63107, which is obviously ensuring that the arc mitigation equipment installed into the assembly correctly works and avoids nuisance tripping, maybe due to switching operations, light signals that optical lights can potentially pick up. Obviously the Archon device has got the current sensing equipment as well, so it uses both technologies, current sensing and light detection, before it initiates any sort of arc quenching during the activation of an arc. So again, all this information is available if you Google Eaton arc faults quenching, and obviously there's lots of information on the Eaton website and the knowledge hub that you can sort of pick up and read on further if you desire. Obviously, there's lots of further reading that everybody can do if you're more interested in the detail. as we spoke about during Tariq's part of the presentation about forms of separation, there's a BEMA guide, which is the British Electrotechnical and Allied Manufacturers Association. So this is made up from independent experts from multiple manufacturers, not only Eaton, but people like Schneider, Hager, ABB, smaller panel builders as well. And obviously there's a wealth of information on the BEMA website, which is all freely downloadable. So there's things like ingress protection, arc fault detection, RCDs, power factor correction, circuit breakers, surge protection devices, a guide to verification, to name a few. And I don't know if there was recently a webinar done by BEMA about the differences between Edition 2 and Edition 3 of 61439 Parts 1 and 2. And also that webinar is available to download for those people who are interested. Then you've got the British Standards Institute, where, for those people who want to go into a little bit more detail, obviously you can download the particular standards. Unfortunately, they're not for free. You'll have to pay for them. But for those people who are designing and building and testing switchgear, it's an essential part, and that's the sort of documentation that you need. So obviously, as Drew and Jamal said earlier, obviously this webinar is recorded and will be available after this presentation, so you can go back at your leisure, and it's free of charge. You can download it for future reference. So let's sort of go back to some of the questions on the chat. So I've got a question here. So obviously, it's a good question here. If Archon is deployed, does that mean a lower PPE could be considered? Yes, of course, this is completely true. Obviously, as part of the arc flash study, it'll determine the sort of calorific effect of an arc flash, and obviously, without Archon installed, the values are high, so the PPE required to work on a live piece of switchgear, again, are higher levels. With Archon, obviously, because the energy of the arc is reduced to virtually zero, and in terms of timeline, obviously the PPE that's required to work on an energised system is obviously further reduced. So yeah, and again, that's one of the advantages of another advantage of applying sort of arc mitigation technology. So there's another question here. Are there any technologies within ACBs that can help reduce arc? Yep. So as I mentioned earlier, Eaton have patented an arc reduction maintenance system, or as we know it as ARMS, on both its ACBs and multi-case circuit breakers. And effectively, this technology, when it's activated, you have to physically activate it. You can either do it via the front panel on the device, or probably more commonly or better employed way of doing it is putting like a contact on a door. So when the door is opened and the system is energized, the ARM system is automatically activated, and essentially what this does, it sort of mitigates a lot of the time delay in the opening of the breaker. So in the event of a fault, the breaker itself opens much quicker, and obviously with the breaker opening much quicker, the arc energy is much more reduced. Okay, so I've got a forms of separation question here. So I don't know if you want to take this one, Tariq. Is there a way of achieving Form 4 separation with a common neutral?
Yeah, the simple answer is no. In order to comply with Form 4, the neutral must form part of either be part of the protective device, or be within the compartment that the protective device fits in.
Okay. And there's another question here regards, in terms of safety, is there any difference between a group-mounted or a compartmentalised way of forms of separation?
Yeah, I think although both means are acceptable. But when it comes to a group-mounted solution, obviously there's always that risk if a breaker sees a fault and it clears the fault, generally it releases ionized gases within an enclosure, and that can obviously have an effect on adjacent circuits. So when you've got a compartmentalized solution, you reduce that risk because obviously the gases are contained within the compartment.
Okay, cheers. Thanks, Tarek. So there's a few more questions, but I can see that the presentation is scheduled to end in a couple of minutes' time. So if there's no questions we haven't answered, obviously we'll get directly back to the guys who are sending the questions in, the ones we haven't unanswered. I'll now sort of hand you back to Jamila, and she can close the presentation.
Thank you, Eaton. Great work. And thank you so much for joining, everyone. We hope you found this very educational. After the webinar closes, you will be directed to a survey. So if you could please leave some feedback, that would be really appreciated. Webinars will be returning from January next year, and we hope to see you then. Thanks again.